Again, I would like to thank organizers for inviting me to this wonderful workshop. And I will talk about normalization of tensor narrow states. I think my talk will have not overlap because from this morning I realized that many things has already talked about by other speakers. But for comprehensive, I will still keep my talk as simple as possible and will also repeat what we have already learned or may not really done systematically, then I will repeat these things. So in the first lecture, I will talk about coarse graining tensor normalization group methods. And so let me give you a very brief introduction on the numerical normalization group. I think you already know this because I think maybe other speakers already mentioned this. I think that the whole field was opened by Ken Wilson in the middle 1970s. He wrote one paper published in Review of Modern Physics. It is essentially a method called the numerical normalization group method. This is still the method used for solving single impurity counter problem. Because this is a single impurity is more like a zero-dimensional strongly correlated system, so I always call this as a method for solving a zero-dimensional strongly correlated problems. Another progress was made by Stephen White, Ken Wilson's student, in 1992. He proposed now we know as the DMRG method. This method works very generally, but it is particularly useful for studying one-dimensional quantum lattice models. And starting from this century, I think different kinds of tensor-based normalization group methods have been proposed. And I think even before that, some people already tried to build up this kind of tensor-based normalization group method to solve some quantum lattice models. And the difference between the normalization group method we learned in quantum field theory and the numerical normalization group method, I think I should say the differences are actually quite dramatic. In the analytical quantum field theory, generally it is the coupling constants, which are normalized in the RG iteration. And in order to have this kind of RG flow be consistent, we need to assume that the system must be scaling invariant. So this is what we learned in the quantum field theory. But for numerical calculations, we get rid of all this kind of running constant RG equation. We directly evaluate quantum wave functions or partition functions directly numerically. For doing this, we also release this condition. We don't need to assume that the system must be scaling invariant. It can be invariant or can be not invariant. So this is the difference between the analytical RG approach and the numeric RG approach. So the basic idea of numerical normalization group method is actually very simple. It is to find a small and optimized set of basis states to represent accurately, for example, a ground state. Just using a very limited number of base states to represent rigorous ground state, for example. In real calculation, this is done by taking many steps of local RG transformation. Here I emphasize local because if it's not local, generally it is not efficient. So this kind of things is done locally. So all the calculations actually is to treat in local tensor or local matrix This is generally have done. So this actually, if we just in a word to say this is what happens in the RG approach, it is actually a compression of phase space, of this compression of information. If we talk to a mathematician, then we will see that what we did here is just to take a lower rank approximation for tensor or for matrix. So this is what we have done. And then one question people may ask, whether the wave function is compressible or not. Now we already know the answer because quite many people already mentioned this. This is the area law, right? Because if we, for example, if we take, for example, this spin 1/2 Ising model, then as example, the total degrees of freedom is 2 to the power L squared. L is the number of sides in one direction. Because of the area law, then the entropy, the entanglement entropy is proportional to the length of the boundary. And in order to catch up the entanglement structure, the minimum number of base states needed, this minimum number of base states needed actually is proportional to the power L, not L squared. So this is much smaller than that. So this actually, the reason we can use this kind of approach to study either quantum system or classical system with this kind of approximations. So what is a tensor network space? This is my definition. First, it is a faithful representation of the partition function for all classical or quantum lattice models. Because for all classical and quantum lattice models, the partition function can be written in this way. Okay? So it can always written as products of tensors. Another definition is that it is a rational answers for the ground state wave function or for some particular wave function for a quantum lattice model. So this is actually just what we want to handle. One is to calculate the partition function or calculate wave function. So this is more like a variation approach. This is more like just directed thermodynamic calculation. So in my first lecture, I will concentrate on how to calculate this quantity. Instead, second lecture, I will talk more how to handle this wave function. So then we ask, in the tensor network, basic RG approach, there's a very important parameter which is a virtual bounded dimension D. Then you may ask how big the D we need, because the area law, then if it's for example in this kind of PEPS wave function, the minimum number of bounded dimension is actually independent of L. So when the bounded dimension is not enough, we should be able to get an accurate description for the ground state. So this is a simple statement. So why this PEPS type wave function is useful, because the bounded dimension is not independent of the lattice size. Then of course this is for the system which satisfies the area law of entanglement. Now how about the system which do not satisfy the area law? For example, the 2D interacting fermions. If you have a Fermi surface, then the entanglement will have a logarithmic connection to this area law. If we still use PEPS wave function, then the minimum number of states needed actually will go in some power law of the system size. Okay. So in this case, this is of course, this means that the PEPS wave function, the D is always not enough in order to describe this system very accurately. Of course, we can get very rigorously. We can always get very accurate results in comparison with other methods. But in order to describe the system in precision, which is we can reach, for example, the machine precision, then in that case, this d must grow in some power law. So this is roughly we know about the tensor nanostates. Then before I go to talk about the coarse gradient tensor renormalization group method, let me make a comparison between the DMRG and the tensor RG approach. So DMRG, of course, works very well for small lattice system. The accuracy is very high. If the system size, for example, is a 6 by 6, then the precision is very high. If we keep, for example, just 800 states here. The problem is that with the increasing of lattice size, the accuracy actually drops almost exponentially with the increase in the lattice size. So, but for the PEPS, the accuracy actually will be better if the system size is larger. Okay, so this is the difference between these two approaches. So this actually gives us hope to say the PEPS is meant to be a better approach for solving a larger lattice system. Okay. So what we need to do with the tensor renormalization group for the classical system or for the quantum system, then one kind of work we need to do is to trace out all the tensors to get to the partition function or thermodynamic quantities. This is one of the goals of this kind of methods. For the quantum lattice model, if we study the wave function, then we first need to, because in this case, for the partition function, this tensor is actually, the initial tensor is null, because we don't need to worry about how to get these local tensors. But for the wave function, these local tensors are variational parameters. So each tensor element is a variational parameter. So we need first to find out determine those local tensors. Then the next step is to evaluate physical quantities. Actually, to evaluate this physical quantity is equivalent to evaluate this trace out all the tensors in the set. So for doing this is equivalent to doing this roughly, just mathematically speaking, they are equivalent. So below I will just tell you how to calculate this kind of quantities. Before doing that, I will first tell you the tensor representation of, for example, a classical statistical models. Of course, for quantum lattice model, because it is equivalent to, for example, two-dimensional quantum lattice model is equivalent to 2 + 1 classical, just three-dimensional classical lattice model. So this is one statement I've already mentioned. Then I will give you an example how to construct this partition function. For example, for one-dimensional lattice model, this is an Ising model in 1D. Then the partition function actually can be expressed as a product of a matrix. Here the matrix is a 2x2 matrix. So this is actually textbook content. So this is very simple. Just express each Boltzmann weight by a matrix. And that's what we need to do here. Then in 2D, this can be done similarly. This is a very simple square lattice. Then the partition function is defined as square lattice. Then we can express this partition function as a product of the Boltzmann weight of each blue square. Okay. Then this actually, this Boltzmann weight actually define a tensor. Itself is actually just define a tensor. Very simple. So this temperature is defined by setting the physical variable as the bound variable. That's what we need. Okay, so it's very simple. So this is actually define a tensor. And this, of course, this tensor network state is defined in a lattice, which is just 45 degrees rotated. And the number of sides here, of the tensor, is actually half of the lattice size. Of course, this kind of definition of tensors is not unique. One can also define the tensor network state in the original lattice. A simple way to do this is to use singular value decomposition to decompose this Boltzmann weight on each bound. So this is Boltzmann weight defined on each bound. Then you can define, use a singular value decomposition to decompose this matrix. Because on all the bounds, then you can do this kind of singular value decomposition, and eventually you can just regroup all these indexes and define a tensor by tracing out the physical variable defined on this side. Then you can have this is a unitary transformation matrix, and this lambda is a diagonal matrix. So this is a definition of tensors. Okay? So this is one way you define a tensor in the original lattice. Again, this is you can have another way to define a tensor. For example, if you can also define a tensor in the dual lattice. Tensor networks in dual lattice. For example, here, this is a square. On each square, you define a dual variable, which is what is spin 1/2. Heisenberg model is very simple. Ising model is very simple. You define new variables. Sigma 1 is just product of S1 times S2, and sigma 2 is S2 times S3, and sigma 4 is S1 S4. Maybe this I don't say this is 4. It's 3 anyway. So the Hamiltonian defined on H plus H is just sum of those dual variables. Of course, these dual variables are not independent. They should satisfy this constraint. Okay? Because the product must be 1. Okay? Then this is actually define the tensor on the dual lattice. So this is another way to define tensor narrow state. Actually, the tensor define the dual lattice and the tensor define the original lattice, they must satisfy duality relation if it's at the TC point. So exactly at the TC point, this tensor should be equal to the tensor defined before, except that there's a constant. Okay, except that there's a constant. So that's actually a duality equation. Okay, there's a dual equation.
Couldn't it be some gauge transformation or the other one?
Yes, you can do this. Actually, I will mention this. This is actually, you can insert any kind of identity operator on each bound and redefine tensors. The partition function is unchanged. Yeah. So, so many different tensor network states. There are many redundant degrees of freedom in the definition of tensors. So you can always choosing a better gauge to do the calculation. Actually, the better gauge generally gives a better solution. So, but we don't know which is better. And that's the problem. You're choosing a better way. For the one-dimensional MPS, massive polar state, that gauge is canonical form. So for the massive polar state, we know the gauge. The best gauge is the canonical gauge. Okay. But for the general, this kind of tensor network states, we don't really know because there are loops. If no loops, then it's very simple. If there are no loops, then it's very simple. Now let's see how can we normalize this kind of tensor network states. Actually, there are quite many different approaches can be used. in 2 dimensions. Classically, for 1 plus 1 dimension. The method first introduced by Nishino was actually quite a powerful method. It's a TMRG method. It's a tensor renormalization, transform matrix renormalization method. And there also this color transform matrix renormalization group method. Yeah. Okay. Later, in 2004, and we dealt this TEBD approach is also a very good approach for handling a 2-dimensional tensor narrow space. And the other approach, a more coarse graining kind of approach, is to coarse grain. The scaling transformation is this is a step by step. This is just block the system size. So this kind of for them, different kind of approaches has been proposed to treat 2-dimensional lattice systems. So which method we should choose? This is generally the problem a student may ask. Of course, when we choose a method, we need to consider first, of course, it's the accuracy of the method, how good this method can be. And then another thing is the efficiency or the cost. If it's you can get a very accurate result, but in 1 year, then you may not have that patience to wait. Another thing which might be important is whether this kind of approach can be applied to 2 plus 1. If it is, then that method can be used to solve 2-dimensional quantum lattice models. Another thing which one may ask is that whether this kind of method can be applied at the critical point, or whether the tensor structure can maintain scaling invariance. So let me just first tell you the efficiency of all these kinds of methods. So generally, the TMRG or CTMRG or TEBD or this kind of approach are the most efficient one. Okay? In fact, here there's a capital D is the bounded dimension of tensors after truncation. Okay? This little d is the physical degrees of freedom. For example, for Ising model, this little d is 2. Okay? So it's mainly determined by this capital D. But in the calculation of ground wave function, because if you put 2 PEPS together, then that little d may not be small. So in that case, this d might be of order d, capital D. So this is the difference between if we really study a classical lattice model or study a 2-dimensional PEPS wave function, for example. And for other kind of approaches, this little d is not important. This is just this capital D here. And generally, the power is higher than 6. And this L is the lattice size. And in the TMRG or this TEBD approach, of course, this is the system size grows linearly. So this is in order to reach that, this is linearly depend on the system size. For other kind of approach, is generally log L, okay, because the system size is doubled every time. And this is the memory cost. Okay, memory cost is not so not too bad even for this case, but this one is a little bit higher. But other cases should be okay. So this is the costs. When you try to choose a method, then you need to consider this factor. Okay. So which one is can give you? Another thing one may consider is that whether this kind of approach can be applied to 3D. Because there are so many choices in 2D. But in 3D, it turns out there are not many choices. All the methods can in principle be applied to 3D. but generally they are very inefficient. The cost is generally too high, and so you may not use it. At the moment, I think the most efficient method is just this HOTRG and HOSRG. Another thing which we should consider is the critical behavior of those kinds of methods. All those kinds of methods, except the bottom two, actually do not have using any disentanglers to remove the local entanglements. So they cannot keep the scaling invariance. Only this NTR, lateral tensor renormalization, and I think Unibly, and also Tao Xiang and NTR. And this method can be applied to handle critical points properly. Okay. So this is the case here is to disentangle, to remove local entanglements. I will not talk about this in detail. I think in the first day you already heard about these kind of things. So now I just tell you a little bit about coarse graining tensor renormalization group, because I think it's here the conceptually I think it's simple, and also may help you to think about how to do this kind of things. If you want to, for example, you want to design a new approach, this might be just helpful. The idea might be helpful. The coarse graining tensor renormalization, for example, if we want to handle tensor networks on a honeycomb lattice, one can do this in 2 steps. One is to reveal this lattice into this one by doing singular value decomposition. This actually by just contracting this horizontal bond so that it become a 4-index tensor. Then you group these 2 index as 1 index in the matrix. Okay, then you define new matrix M, which is have a 2 index, but this is this 2. You think this is 1. Then do a singular value decomposition and stretch this point into a bond. Okay, separate into a bond. So this is by doing a singular value decomposition. Of course, the bond dimension here is thick bond dimension, which is squared in comparison with the original bond dimension. So we needed to, in order to carry out this RG calculation step by step, and we need to do truncation here. Now the truncation, we just take approximation and we just keep the largest D singular values. So this becomes a thinner bond again. Then the next step, next step is just to contract this internal triangle, the bonds. Then it just becomes a point. So from next lattice, we return to the honeycomb lattice by reducing the system size by a factor of 3. So this is actually very simple. This procedure, if we just coding these kind of things, I think 109 is enough. If you use, for example, use MATLAB, very simple. This is actually the accuracy. If you keep 24 states and accuracy for the Ising model for the free energy. So it's reasonably good. But of course, this accuracy can be further improved by considering the environmental contribution. Because when we do this kind of calculation, we optimize just this 2 tensor. This is local tensor, without considering other tensors reaction, right? Actually, what we really need to optimize is the partition function, okay? It's not just this local tensor. This is a local tensor. So the TRG approach I talked about is just a local optimization approach. In order to optimize this partition function, we also need to know the contribution of this environment tensor. This environment tensor is just all the tensors, rest of the tensors, just excluding those two tensors. Okay. Of course, we don't really know how to calculate this environment tensor exactly, but we can do this and approximately. For example, using just a method then from TRG. Okay. Then if we know this tensor, then we can have a better optimization scheme than to do the truncation. I call this a second renormalization approach. Then the key question here is how to calculate this environment tensor use approach I told you before. So that's actually the trick. The whole trick is actually you can do this in two ways. One is very simple, because when we do this kind of single value decomposition, we also get a bound vector, the lambda. We can also put this lambda on every bound, okay? Which assume that this is some kind of entanglement being filled acting on each bound. In that case, this being filled approximated environment can be just set as the bound on this doubling bounds. Okay, so this is actually obtained just from here. This is like a take a mean field approximation. Of course, the mean field here is just entanglement spectrum. If we just think of this as an entanglement spectrum. So this is a definition for the environment. So it's very simple. This is something like a mean field approximation, or like a cavity approximation on beta lattice. This can indeed improve the results. Okay, accuracy. This is very simple. You just put there and do the calculation. This is actually a critical point. So at the critical point, the improvements there is relatively worse in other parts and improve by more than one order of magnitude. Of course, one can do a better job to trace out all these environment tensors. Okay, this is by doing one step of TRG. Okay, then this environment tensor or environment lattice become this kind of environment lattice. This is always bounding bounds, okay? Because there are no sites there. This, of course, you can do this step by step. Just follow the step of TRG. In general, this is one. You're starting from this environment lattice, then go to this one, then you contract all these triangles, then it goes to this one. If you compare this one with this one, they are actually similar, just rotating 90 degrees. Okay. Now, if we separate this part, separate just this part, then the rest of the part is just this one. They actually have a similar structure as this one. Okay. So now you can do the coarse graining transformation for this part again. So there's an iterative relation, a recursion relation between this larger environment tensor and coarse grained environment tensor. So you can always found this coarse graining tensor by doing a forward iteration and then do a backward iteration. Okay. So this is actually the trick for evaluating this environment tensor. a little bit more involving well, encoding especially, but it's doable. It's not that complicated once you know how to do this. But this actually formula is very simple. It's not that complicated. Then this is actually a comparison. If we do more better calculation, then the improvement in comparison is TRG. Except if it's away from the critical points, then the improvement gets bigger and bigger. But at the critical point, the improvement is still not that as good as away from that critical point. So this is give you a rough idea of how good this method can be. And of course, this kind of approach is okay, but it's very difficult to be extended to 3D. Now I just tell you an approach which can be readily extended to 3 dimensions. This is a coarse gradient tensorization by taking higher order singular value decomposition. Okay. Here I just started from 2 dimensions. This is a tensor narrow states. In this case, the coarse gradient is actually very simple. You just contract every 2 sides, for example, along the vertical direction. Just form a new lattice. This is a 4x4, then this is a 2x4. Okay, lattice. Of course, this once you contract this 2 tensor into 1, the horizontal bound dimension is squared. Now we need to do from the approximation to cut this bound from d squared to d. So this is to do this one. This is done by taking higher order singular value decomposition. This is directly singular value decomposite every bound. But here only the horizontal bound needs to be decomposed by taking this horizontal, by taking this singular value decomposition. Okay. This actually can be done very easily, not that difficult. So this is you define a new tensor. This is x actually is contains 2 index. This x1 is 2. This is x prime contains another 2. Okay. Then do a singular value decomposition. The higher order singular value decomposition is to decompose this tensor into another tensor which is called core tensor, and with 4 unitary transformation matrices. This is called higher order singular value decomposition. And the next step is to truncate this horizontal bound. Okay. Just renormalize this from this unitary matrix. So it's very straightforward, not very complicated. So the difference between a matrix singular value decomposition and the tensor higher order singular value decomposition is that in the matrix, this is a diagonal matrix. But here, this is not a diagonal tensor. It is still a full rank tensor. But it satisfies this kind of properties, this core tensor. That means that if you contract all the indexes except this, the second index, then they should be orthogonal if this j is not equal to j prime. So that means it's a coarse diagonal. It's not exactly diagonal in the tensor sense, but it is a coarse diagonal. Another thing is you can order this kind of tensor elements so that this absolute value of the tensor elements is actually not elements, it's actually the product of these 2 things. First, you take a j equal to j prime and take a square root. And this is the absolute value of that subtensor. Then you can always order these tensors in a way that something that you order singular values in a descending order. Okay? this is a very like diagonal singular value matrix. But here, this is not really diagonal matrix, diagonal tensor. But it has some properties of singular values in the matrix. Okay, I will skip this. So the whole structure for doing this HOTRG is something like that. You're starting from this two tensor, then they form a new tensor, big tensor, then you do a truncation. This is using a unitary transformation matrix, isometric. Then they form another one, this tensor. Then they can do this along horizontal direction. Then you can also combine this tensor and form another tensor and do this kind of iteration. Because this is the diagram first drawn by Nishino, so I call it the Nishino diagram for this kind of actual TRG. Okay. I think Nishino already fall sleeping. Anyway, so this idea can be also used to calculate, for example, to construct the corresponding SRT approach. But here it's just have a hole of two sides, and the rest of the part is just environment. Then of course, the next step is to calculate this kind of environment tensors using this forward-backward iterations. So this is forward iteration is actually simple, just like do this kind of TRG calculation. And backward iteration is to calculate this environment. You determine this EN. EN is the environment tensor here for on the n step. But you first determine this EN plus 1. This also the environment tensor is the next step. So this is the iteration formula. Very simple, I should say. Because all these kinds of tensors, U and T, are actually already determined when you do this TRG calculation. So you just group all these tensors together, then using this formula, you can determine the tensor for environment tensors at every step. Of course, when you determine this environment tensor, you can calculate the bounded density matrix then to do the calculation. So I will not go to detail here. And if anyone wants to know how to do this, then we can have a discussion privately. Now let me give you a comparison for different methods. So how good this kind of method can be. Then from here, you already say this. CTMRG, ITBD is much better than other approach. Okay. So this is machine error. So otherwise, this curve should go this way. Okay. Only around the critical point, the difference is not that significant. Okay. And also, I should point out that if you just use CTMRG or ITBD, the accuracy can be even get better because the decom can be much bigger. Okay. So this is this can give you a rough idea so what kind of approach you should use for doing these kind of things. But this doesn't mean this accuracy may not mean that it also mean the efficiency, right? Because a different method maybe. But in general, all this kind of approach can be used in the study of two-dimensional classical models. But if it's away from critical point, generally I recommend CTMRG or GED. Okay. The trouble is that those kinds of approach are very difficult to use in 3D. Only those HO can be used in 3D. So now I just tell you a little bit about 3D.
Question.
Yeah.
So in this plot, CTMRG and ITBD shows almost the same accuracy, but
Yeah. That means
right-
almost exact for the given D.
Oh, I see.
For given D.
Okay.
That's already reached their limit. The method. So that means you cannot prove that method by keeping the D unchanged to say that the accuracy will drop.
May I ask a question?
Yes, please.
So, by comparing the TRD and HOTRD,
Yes.
HOTRD has a good accuracy.
Yeah, it's better than this one.
Yes.
Because if you just simply count the entanglement, you see how many bonds they cut. Actually, DRG cuts less bonds, so that's why it's more accurate. So generally, if you construct a method, you should cut as least as possible bonds as possible. That will give you a better approximation. Now I just go to the 3D. So in 3D, this HOTRG approach can be easily extended to 3D. The cost, the increase of cost is very limited. So the idea is similar. Okay, just contract to tensor every time. For example, first along this vertical direction, next time along this horizontal direction, this next time around is x direction, y direction, z direction, just rotating this kind of contraction. So every time you found there, you kind of do a singular value, higher order singular value decomposition for tensor, then you determine core tensor, then do truncation. So it's very simple. So this step is straightforward. You can generalize from 2D to 3D. Okay? It's not that complicated. If you understand how to do this in 2D, then the 3D is straightforward. So I will not discuss about this in detail. So this is cost. In comparison with 2D and this is 3D, so the memory increases by d squared, and the cost by d to the fourth. Okay, so that's actually. For other methods, generally this is the exponent. Generally, is more than 15. Okay. So this is why this kind of approach is relatively more efficient than other methods. For example, if you consider CTMRG, three-dimensional CTMRG can do this, but the cost is very high. Now I just give you, show you some results obtained with this HOTRG 3D. Okay, the three-dimensional Ising model. This is magnetization as a function of temperature. On the same plot, we will also show the results obtained by Monte Carlo simulation. Okay. This is by keeping d equal to 14 in 3D. And actually, you will not see the difference between these two kind of methods, Monte Carlo and HOTRG. The relative difference is less than 10 to minus 5. So if you want to see this difference, we have to enlarge this by 5 orders of magnitude. And this is for the specific heat. Also comparison with Monte Carlo. Also the difference is almost negligible. You can see the difference in most of the plots, except here and some deviation. Generally very small. And this is entropy, and we can also calculate entropy. To Monte Carlo, there's no data from Monte Carlo, so for comparison. Again, this is for the 14. Of course, from this kind of singularity, we can also determine TC for the Ising model. Okay? We can determine it either from here or from here. Okay? They are actually, the differences are very, very tiny. Then this actually, the TC we determined from this kind of calculation. And this is actually from magnetization, also from specific heat, they have together almost exact same results. So I just showed you the data. And at the beginning, still show some oscillation, but eventually it almost converged. It's not exactly the same, I should say, just because the difference is tiny, so you cannot see the oscillation here. Let me just give the number, this number and this number. And you will see how accurate it can be. This is the result we obtained in 2012, as up to this digital number, converge the number at many. And this is 2 years later, then we enlarge this bond dimension to 23, then we get this a few more digital number. So this is a comparison with other kind of approach. I think the most accurate one is Renormalization, this one. I think essentially we agree with each other. I think maybe we already have a better accuracy than Renormalization. And this is a high temperature expansion. This is also we should mention that we should also did HOTRG calculation many years ago. In that case, his D is only, I think it's 2 or 3. So for 2, I think it's reasonably okay for this value. Unfortunately, he didn't do this for larger bond dimension because I think it cost more to CPU time to do that. So this kind of approach, as I mentioned, can be also applied to 2-dimensional quantum lattice model, because the 2-dimensional quantum lattice model is equivalent to 3-dimensional classical lattice model. So we also tested this kind of approach for this quantum Ising model, 2D quantum Ising model. This is just transverse Ising model. It's Ising model with transverse field. So this is, unfortunately, we do not have other numerical data for comparison. We just show the data here. Okay, and the critical field we obtained, I think, essentially agrees with Monte Carlo and other approach, but we don't know whether this is which one is more accurate because we do not have comparison. We just do one big calculation, and actually we should do more and then see to get a better result. And then essentially this shows that with this kind of approach, you can get very good data for even for quantum lattice models. This is actually for the same model, but we show how the internal energy changes with temperature at a different field, and how the magnetization, the phase transition happens at final temperature at a different field. Okay. So just show you some curves. Okay, so here I just, as I hope I just give you just a brief idea how the method works and the different kind of method works and how good they are and what kind of method we should choose if you want to use this kind of method in your future study.
I have a question about the
Yes.
question of the transition field about the two-dimensional transverse field Ising model.
Yeah.
That's it. That HC has only 3 digits. Basically, three-dimensional Ising model, two-dimensional quantum Ising model can be obtained as an anisotropic limit of the three-dimensional classical
Yeah.
model.
Okay.
So if you take some, it with some anisotropy, you can automatically reach to that two-dimensional quantum model. So what is the reason that you obtain less accuracy for HC compared with DC in three-dimensional case?
You mean this value is less accurate than this one?
Yeah.
This is exact? You mean?
Pardon?
You mean this Monte Carlo result is already exact results?
Maybe he's comparing with this quantum system, 2D quantum system with three-dimensional classical system. Three-dimensional classical
Oh,
system,
right.
you,
Oh, sorry.
you got
Oh, no,
digits.
I understand. Because here there's a total error. There's a total error. There's a total error because we didn't do the extrapolation for the total error goes to 0. We didn't take that limit. Yeah. Okay. Sorry. I misunderstood the question. But here, this is I forgot the value. I should write down the total tau. I think it's 0.05. I think something. So that actually limits this accuracy. Also, we didn't do this calculation very carefully around these points. So there's another reason. Because in order to do this very carefully, then we need to spend a lot of time to go around these points. And also increase this, see how the boundary dimension dependence and also the total parameter dependence. Okay, I talked about this local tensors and how it flow in RT. Now I just discussed about how this local tensors changes at the different step of this coarse graining. So if we have a tensor network model, for example, Ising model, if we do the calculation, then the local tensor should flow into the local fixed point tensor, either to the low temperature phase or to the high temperature phase. So the tensor should choose either one of them, okay? Depend on the starting point, whether it's on the right-hand side of the critical point or the left-hand side of the critical point. So that tensor eventually will converge to some of the fixed point tensor. It should be, after convergence, it should be the same. The tensor should be the same up to a gauge inverse. Okay. Now let's just say, for example, if we do this HOTRG, then every step we just do a contraction. And if this step of RG step were becoming very large, then this tensor should converge. Independent on the initial tensor. Okay? Just ignore the initial, what was the initial state. Okay? Where the temperature is, then the final tensor should be just goes to, for example, from the right-hand side, starting from the right-hand side of the critical point, then should goes to infinity temperature. So that tensor should have the same structure as the infinity, the tensor for the infinity temperature. After convergence, the fixed point tensor should contains no entanglement. So it becomes completely disentangled. Okay, so that's actually the message. For example, for the critical point, just this Ising model, if it's an altered state, the convergent tensor actually has only two non-zero elements. This is actually diagonal tensor. It has only one. Okay? Just because the ground state is doubly degenerate. Let's see. Okay. It's a Feynman up, the Feynman state point up spin and also point down spin. So there are two kinds of ground state. So the converged tensor or fixed point tensor is just one. If it's a disordered state, then it's just one. There's only one non-zero tensor element. Of course, this is not true in the real calculation because there, as I mentioned, there's gauge invariance. So if you just add any kind of gauge transformation, this of course will become become a 4-rank tensor. So you will not see this kind of structure directly. So this kind of things can be actually read out by construct, for example, just a gauge invariant parameter. You define a gauge invariant parameter for them x here, which is defined by trace out all these tensors. Let's go this horizontal direction and vertical direction. Assume it's pure rate boundary condition and trace out and square it and divided by these two tensors. Okay, if we contract these two tensors, then eventually you will find that this is how the tensor, just this value changes with iteration. For example, this is if it's a fourth step of NRG, just HOTRG. So this is this curve. If it's 8, then it goes to this 9. If it's 12, it goes away. Then if it's 16, it goes away. If it's keep going, then it will become converged. Then this value will become exactly 1. Okay, the high temperature, above critical temperature, then become 2, and below the critical temperature. So if it's very close to, the temperature is very close to the critical point, of course you need to enlarge the steps of the number of iterations in order to disentangle that tensor. So after disentanglement, where eventually just become that value will become exactly 1. So in the limit, this is n goes to infinity. This should just a straight step function. So go this way, just step function.
I have a question.
Yes.
If there is a corner double line structure
Yes.
in the fixed point tensor,
Yeah.
this quantity is similar behavior.
No, this is just precisely just corner double line, just precisely just a step function.
Okay. This quantity cannot distinguish the corner double line tensor and perfectly disentangled tensors. Corner double line tensor has a
Corner double line. I mean, after you go to the converged, after doing RG, you get a converged or fixed point, then they are the same. The intermediate step, of course, they are different. Right? Because here, as I said, if you just do the calculation up to, for example, 12 iteration, then you will see this, which is not called double line, neither just this is just a step function. Right? Yeah. Please.
I think the contribution from the corner double line structure
Yeah.
is totally cancelled between the denominator and
Yeah, yeah, you're right. Yes, but not totally cancelled, because if it depends on how many non-zero elements. Okay, so this is, in this case there are 2 on this side, so this is 2, because it's a square, 2 square, and then this is divided by 2. So let's give you 2. Okay. If it's for example, ground state is degenerate, if it's degeneracy is 3, then the denominator is 3 squared, then divided by 3. That gives 3.
So does this satisfy the same scaling behavior as the Binder parameter?
I don't know. That's a good question. Maybe not. Maybe not. I don't know. I don't know the answer to that. So this is certainly very similar to Binder parameter, but not exactly the same. Okay. Of course, this is how the flow of the, because you always, this is kind of, for example, in this calculation, you can define the singular value decomposition. Now, of course, you can always normalize this singular value values. So if we set lambda 1, the top one is 1, then this is how the second largest singular value evolves with RG flow, RG steps. So at the beginning, of course, you will not see much difference. It doesn't matter whether it starts from what kind of temperature. because of the difference between different points, the temperature is very, difference is very tiny. So you will not see much difference at the beginning. Eventually, they will separate into two parts. One flow to 0, one flow to 1. Okay? So this is the second. The second one will become degenerate with the leading one, so it becomes 1. And if it's in the high temperature, then you flow to 0. Okay? So this is kind of tell you very accurately. If you want to determine TC, then you will say you can just change this parameter and say whether it's a flow up or flow down, and that'll give you a TC.
Could you explain the definition of verticality?
This is because when we do this when we do the RG calculation, we have a singular value spectrum. We do singular value decomposition, right? The singular value spectrum, then we normalize that so that the leading one is 1, then this second one. Because this parameter is gauge invariant, so that's what I should say.
What happens if there is a tiny symmetry breaking field? So if it was a very big external field,
Yes.
then what happens upon this line?
It's similar. Once you have a two phase, then generally you will either flow to one of the phase or flow to other phase. So this number just depends on what kind of phase you have. If you have a tiny difference, that means that upspin, downspin may not be fully degenerate. This is what you mean, right?
Yeah,
I don't exactly know. We didn't try that. That's a good question. I think maybe this value will flow to, for example, 0.99 something, maybe not exactly 1. That could be. Yeah. Good question. Yeah. But I think in high temperature it will still flow to 0. Only the upper one, maybe it's not exactly 0 because it's not a complete degenerate because upspin, downspin may not completely degenerate. In that case, maybe it's a flow to, for example, 0.99 something.
Can you relate the value of this lambda 2 to some scaling dimension or some?
Yes, I will show you.
Okay.
Okay, this is for 2D. Similarly, you can do this calculation for 3D. Okay, so you will also see this kind of flow, different kind of flows, right? If you have a 3-phase transition, or more than one critical point, then you will see this. Maybe there are more steps between. Okay, in some cases you can have that's a step function. We have this kind of step function. Okay, but here around each critical points, you will see they flow to two sides. Okay? So this is very clear. So although this kind of method is not a critical, doesn't scale invariant, but you can still read out quite many information about critical points.
I have a question.
Yes.
If we use more large bond dimension D,
Yes.
the branching point will be shifted.
Second.
Yeah. In this case,
Yeah.
about the 27 renormalization step is the branching point.
All right. It depends on how close you are at the critical point. Because we don't know exactly critical point where it is, right? So we just choose close to critical point. So if exactly at the critical point, then this one may go very low. So you mean where this began to split? This is what your question, right?
Yes,
Yeah. So this is just because we choose the temperature. Also depends on how small the temperature difference between the temperature we used here and the exact critical temperature.
Does it depend on the bond dimension?
Not much on the boundary dimension, but on the critical temperature, how far away from the critical temperature. Yeah, if it's exactly the critical temperature for that bound dimension, because different bound dimension have different TC. Okay, if you exact it, for example, like TC, then this will go forever in principle. Okay, that's actually where scaling invariance happens. Of course, you cannot guess the temperature so accurately, so it will always goes to sides. From this kind of calculation, you can, of course, you can read out different kind of informations. For example, one of the information you can read out is just the central charge. Okay, you have 3 points from the charge. The reason is that just because if a system size is not infinity, then it's always the size is always smaller than correlation x in the critical point. So that's critical. The system is still critical, right? Although, of course, in that case, system size is not enough, then it will not flow to either of the fixed points. Okay. So this is the reason we can read out some critical information from this calculation. And for example, if we calculate this matrix, the eigenvalues, then we can read out the tensor, or read out the critical. This is central charge. So this is the second. This value. Okay. This is just the maximum eigenvalue of this tensor after renormalization. Then this value, if we just at different temperatures, at different step of iteration, then you are saying these kind of things, then the convergence point is here. It's very accurate for Ising model. Very accurate Ising model. It may not be that accurate for other models, but certainly Ising model is very, very good. We tried this for XY model. It's not that accurate, actually. We did not see this kind of very precise cross points. So this is, anyway, this kind of approach can indeed give us some information. Although the approach I just mentioned, this is not very accurate at the critical points, but still we can read out information.
Sorry. When you say the XY model, you mean the equivalent of the Heisenberg model, the classical?
It's a classical XY model.
And what is the quantum?
It's just a continuous model.
But is it so? Is XZ at the SU2 point, or is it?
It's yes. Yeah. Just
so maybe the reason why you don't get C accurately because we have this logarithmic connection.
Yes, that's the problem. Yes, you're right. Yes. Because this is a KT transition, the singularity is not that strong. That's a problem. The logarithmic corrections make these things not crossing at one point. All right, yes. We hope we can just treat it better, but unfortunately we haven't get any result which is really worth to show here. Okay, because show this. For this particular model, this seems to be good. Okay, I have 15 minutes, right? Okay, let me just take the rest of the time just to show you one of the results we studied using this kind of approach to study, for example, our classical model. It's a post model on regular lattice. We just hope we can solve a problem which hasn't been solved before. So that's actually our mission. So eventually, we found a model which has been studied for many years, but no one got any conclusion. And this is on the post model on the irregular lattice, and this is a post model. It's an extension of the azimuth from q equal to 2 to any number. Okay, so this is q. This is the basis state on each side. So this is very simple, extremely simple. And this model was proposed in early 1950s, so already more than 60 years. And many properties of this model are known. For example, if it's anti-family coupled, then we know that there's a critical QC. There's a critical. In that case, if Q is smaller than this QC, it has first or second order phase transition at final temperature. If exactly the Q equal to QC, then the system becomes critical at 0 temperature. If its Q is larger than some value, then there's no phase transition. So this is none. The problem is that is how big the QC is different on different lattices. For example, if honeycomb lattice, then this QC is less than 3, more than 2. Okay? Of course, 2 is there's a phase transition. And a square lattice, this is exactly 3. Dense lattice is more than 3. And Kagome lattice is exactly 3. And a triangle lattice is 4. It seems that none of the lattice can have a value which is more than 4. Okay? So we just ask question whether we can find this kind of model which is more than 4. Okay? Then we just take this lattice as the first. We try this one. Eventually we found that all this kind of model actually except have this kind of approaches. This is a Union Jack lattice. Union Jack lattice. This is a British flag. It has 3 sublattices. One of the sublattices has only 4 labels, and the other 2 lattices have 8 labels. 1, 2, 3, 4. So this is the difference between different sublattices. Then because of this, the number of coordinates are different, then you will introduce some kind of geometry frustration. Oh, actually, entropy frustration, I should say. And this system, if you analyze the system, you will find that this system in the ground state must have some kind of symmetry breaking. But that symmetry is not this kind of symmetry breaking. This is like a ferromagnetic state. You have 40 symmetry, the whole lattice become symmetry breaking. Actually, in this system, we can have this kind of partial symmetry breaking. It becomes, for example, ferromagnetic only in one of the sublattices, but not in the other sublattice. It can be in the, for example, in the blue sublattice, or green sublattice, or in the red sublattice. So there are 2 choices. You should either choose the red sublattice or green sublattice. And also, because this is, if you choose just one, then the spin on this sublattice and on this sublattice can be pointed in arbitrary direction. So the ground state is highly degenerate because it can have arbitrary random directions in this red and this yellow sublattices. So it has very big entropy at the null temperature. So that entropy will driven the system into an ordered state, which must show this kind of partial symmetry breaking. So this is a very simple physical argument. We can also calculate how big the entropy in the ground state.
I don't the Hamiltonian is the nearest neighbor.
Yeah, that's right.
And
with also have this kind of relations.
but I don't understand how you can get a ground state that doesn't depend. So if you flip one, go to the next slide again. So here it looks like, so the green dot talk to all yellow and pink. No?
That's right, yeah, because you have a 4 choice, right? For example, this is the choice, the sigma equal to 1, then this can be 2, this can be 3, right? If it's just a Q just equal to 3, then you have this fixed, the ground state. But if it's 4, then you have more choice. So this is just because you have is more than spin 2, this is spin equal to 4. Have 4 basis states. So you can actually do a very rough estimation, say how big the entropy at zero temperature is roughly given by this number. Okay? So the key information is that it's proportional to the number of lattice sites. Okay? And then if we just say, if only the red and green sublattice are ordered, then ground state actually is going to put degeneracy, then should be this number. So this is actually the degeneracy. And this number is just because you can have a red or green sublattice, you can order it arbitrary way. So this gives this number. You have two choices to choose red or choose green sublattice. So you can also, we use this kind of for coarse graining approach to calculate the entropy. Then we will see that is indeed very close to this ordered phase states. Okay, we show these kind of things. But of course, just from this entropy, we cannot see any kind of phase translation. It's very difficult to see phase translation, where the phase translation happens. But we believe that there must be a phase translation in the system. And actually, this critical point actually is, has two kinds of singularities. One is ordered to disordered states. It's going to be like an Ising model. Another one you have a Z2 singularity because it's blue sublattice. So you have two sets of critical exponents, not just one, not like Ising model. One. That means you have two sets of critical exponents. Now we try to find these critical points using just the method I introduced. We do the calculation for specific heat. Then when we first do the scan, of course the step is relatively big. Then we cannot see any kind of singularity. Then we just can just concentrate on this point. We found some in the calculation. There are more data, so we found that actually around here, it seems that the curve becomes nice smooth. As smooth as one, and then we just enlarge this part. So indeed, there's a phase translation points. Okay. Once we found that, of course, you not just points, then you have many methods which can help us to find these kind of things. For example, now we realize that we can calculate this, for example, the sublattice magnetization. Now immediately we see that. And of course, the numerical can be also used to calculate this kind of if you know there's a phase translation, then there are many approaches which can be used to.
In that term, where is the real singularity?
You mean here?
Really?
Here, because this is a bounded dimension. Right?
Ah, I see.
But here is more clear. There's a thing. It's not here. Of course, you are saying, well, this is smooth. Yes, it is a smooth function. But if you increase the bounded dimension, this will become steeper. Here, just show you that this point there's a better way to find this point. Because at the beginning, we just calculated specific heat. It's very difficult to fix that point. But from this magnetization, sublattice magnetization, actually, we can, if we do this first, then we can already just see the point. And actually, this happens on all these kinds of irregular lattices. For example, this is checkboard lattice. Also have different kinds of sublattices, and they are not equivalent. Then you will also say there's a small jump here, very tiny. So indeed, we need very accurate methods, like CTMRG or the other kind of. I think this is obtained by HOTRG, I think. HOTRG is also accurate enough here. And this is for dense lattice. It has two kinds of sublattices. So this is 3 neighbors, and this is 6 neighbors. So we always see this kind of entropy-driven. This is entropy-driven business. And also this center depth lattice. So eventually we just ignored this table, and we found that actually unit-check the number must be actually marginal 5. Actually, I didn't show you all the results. This is also marginal 5.
May I ask
sorry.
a question? So
Okay.
in this case, the phase transition of the first order.
This is yes, you're right. For this one is the first order.
Okay.
Oh, actually, it's second order. Sorry, this is a
Second.
specific jump. The jump in the specific. There's no jump in the entropy. Entropy is smooth.
Second.
In second order. Sorry. This is like to be the first order. This is
Sorry?
entropy.
At zero temperature, when you look at the entropy,
Yeah.
this is antiferromagnetic, right?
Yes.
So it should kind of map to the coloring problem, no?
Yes.
You're basically counting all
you can.
configurations.
You can. Yeah.
So do you get the finite entropy at zero?
Yes. Yes. Okay. So, actually, this number we got first
That was
by
the
coloring.
number. Oh, okay.
That's why I mentioned I didn't discuss about the coloring model, but their equipment. All right.
So
Okay.
what kind of symmetry is broken here?
The symmetry
Yeah.
is one of the symmetries. This is Z2 symmetry, as I mentioned. Is the right sublattice and green sublattice. Is one of the symmetry breaking. Another one is just this ordered and disordered states. Because this is in comparison with the disorder or paramagnetic phase. This is the ordered phase. This is also ordered phase in comparison with high temperature disordered phase. So this is like a sublattice S in transition and plus Z2.
So the both kind of symmetries are broken at the same time, or?
In the same time, just because there's only one critical point.
Oh.
It happens, you have two critical points.
Uh,
I didn't show all the figures here. I think for this sublattice, if I remember correctly, this is q to the 5. If it's q to the 4, then either it's q to the 5 or q to the 4. Then there are two transition points. There are two phase transitions.
I see.
I didn't show all the figures here. Yes. So in some cases it happens simultaneously, in some cases separate. So, okay, let me make a brief summary. And I think in the past decades we have tried to just develop this RG method in order to calculate Tensor states. I think this method provides a powerful tool for studying 2D or 3D or 2+1D lattice models. But I think there's still quite a few people using this kind of method to do real research. So I hope more and more students can really use these things in the future. Okay, thank you very much. Okay, so should we just close the lecture?
Yep. If there is no question, sure.
Okay.
You said that in the application to the Ising model, two-dimensional Ising model,
Yes.
CTMRG has the best performance for the calculation of free energy contraction tensor network.
Depending on where, actually, I didn't show the result for example,
Okay.
exactly at the critical point, then actually loop T or loop NTR, actually,
Yeah,
exactly
yeah.
the critical point.
But if we do the CTMRG or ITBD type method, then they have
They have better best.
better. So in real study, as you showed in the anti-parabolic model can be
Yeah.
applied at CTMRG or ITBD type method.
Yes, in Tensor, yes.
Yes.
Yeah, same.
So why didn't use the CTMRG or ITBD?
Generally, the reason, of course, is just we first tried this one, and so we already found the results. So, but in principle, yes, you can always use CTMRG to do that. Right? It's cheaper, and also you can get very accurate results. I think the one of the curve I obtained is actually obtained by using PEPD. So. Exactly at a critical point, I think Loop TMR actually can get a better result if you use the same D. But I should still mention that if you use CTMRG or ITBD, you can get a larger bounded dimension and do 1,000. So in that case, I think in 1,000, I think accuracy is true. Okay. So let's give a rough idea. But in some cases, CTMRG may not work as good as other method. If, for example, it's quarter and edge metrics are not symmetric. Okay, in that case, the accuracy will drop. So one should be more cautious when you use these kind of things. Because if the left and the right eigenvectors are not exactly conjugate themselves, the density matrix will become non-symmetric. That will cause some trouble. Yes.
So in the last section, you discussed union jack lattice and so
Yes.
on. Did you call them irregular lattice?
All right, yes. This is not I call it. It's actually in literature people call it.
You mean unconventional lattice?
It is no. It's if you, for example, this kind of lattice generally called regular lattice, hardcome lattice, a square, Kagome triangle. If you have only one sublattice, just one sublattice, all the sides are equivalent. And we call this regular. Or actually literature, we call it regular.
So when you have inequilibrium sublattices,
they also call it Archimedes lattice. And this kind of lattice, other lattices are called, there's a name, I can't use PEG lattice or nav lattice. I can't remember, but anyway, they have some kind of naming.
Maybe my another question is, can you have someone applied this kind of method to random lattice or
Yes.
some random system?
Yeah. Yes. For example, spin glass. There's one paper published by a Chinese group in Beijing. They studied spin glass. Two-dimensional spin glass.
So you construct the tensor
Just
starting from
every
the-
tensor are different.
Then construct the tensor from the strongest interaction or something?
No. They just do this locally, every two.
Oh, okay.
So, not like the older approach. Okay, right.
If there is no further question, thank you again.